Today we will start the DC motor speed control. We will talk about the separately excited DC motor control speed. Okay. So, speed control of DC motor. Okay. Any speed control we require a reference speed. For last time when we are talking about the front end AC to DC converter, the reference was DC link voltage, output DC voltage. Now the speed is the reference. So this we will represent it like this. This is our speed reference. Okay. So speed reference, I will put it as NR, speed reference. Okay. The moment speed reference means it has to be compared. We have to check whether the system has acquired the correct speed whenever there is a change in the input reference. That means whether the input is following the or the output is following the input. So, we will correct control. Here is the speed feedback. We will represent as F feedback. Now we require a controller. So we talked about various controllers, classical controllers used P, PI, PI, PI. So we will decide which controller is required. So here we will simply write now controller. What this controller should do? This controller output will vary whenever there is a mismatch in the speed reference and the speed feedback, and we are controlling the DC motor. So DC motor speed we are how we are controlling? We are controlling by controlling the armature voltage, input voltage, and this is we are through a converter. Let us take a phase control converter. Then we have to control the firing angle. So this output should, if with cosine comparison, this is the control voltage, it should go to converter. See, I am generally saying converter. You can have phase control converter or front end AC to DC converter or our 4-quadrant chopper, whatever it is. Okay. So converter. This converter output, that is a variable DC. It will go to our motor. This is our motor, and motor will have the tacho. So from the tacho, we will measure the speed. So tacho voltage will not be perfectly DC, and it will have ripple. So we require to filter it out, and a gain change is required. You have to bring it to the controller level. So this is feedback signal processing. Okay. So basically this is a filter, filter with a gain control. So we have to control the ripple also. So this is signal controller, signal processing. So we can put it as filter. Because tacho will not be perfect DC, and if it be DC, this voltage we have to bring it to variable speed. With the different speed, the voltage is different variation will be there. So we have to bring down to the controller level. Controller level, as I told before, let us take for with analog controls, we are working with +10 and -10, and also we want perfect DC here. So if there is a ripple is there, you have to filter it. So we put a filter here. Now the question is how to design our control. We should have a input output relation. That is a transfer function, frequency response model, that frequency dependent model of the system. Then we can, based on that one, we can find out the total input output relation, output by input ratio, that is a transfer function. From there we can design our controller, so that it will give optimum response. So where we will start? Let us start with motor. We have not got the motor model now. Okay. So separately excited motor. So we will start here, motor model. So, this we can represent, this is our armature resistance Ra and leakage resistance La. Then here we have the back EMF Eb here, and here also the field winding, we are giving the required field winding, free field current, rated field one, keeping it, we are not disturbing that one. We are only controlling the armature voltage VA. Okay. This is plus minus. Okay. Now, we have to find out the transfer function. So, here VA is equal to our IA, armature current IA, RA plus LA into dIA by dt plus EB. We know that VA is armature voltage, okay, the armature voltage, which we are controlling through our converter, and back EMF we have studied is not in our control, it depends on the speed. This is the back EMF, motor back EMF. IA armature current due to our applied voltage, current, RA is the armature resistance, L is the armature inductance, winding inductance. Should be in Henrys. This should be in volts. This should be in volts. This also in amperes. This should be amperes. This should be amps. This should be in ohms. This should be in Henry. Okay. Now, let us write down the equation between VA input and the motor parameters. Now, we are basically controlling the speed. So, in the previous equation, speed we have not brought in. So, here we have to bring the torque. So, the driving torque which is supplied from the input power divided by speed. So, driving torque MD is equal to J into d omega by dt, that is angular speed in radians per second, plus our load torque, that is our load torque. So, here J is the, ML is the, if you see, ML is the load torque in Newton meter. This is in Newton meter unit. J, how to find out the J? We have studied in the initial classes, moment of inertia of the whole system. J is equal to moment of inertia, moment of including the load, the complete system. This will be kilogram meter square unit, omega angular velocity, in radians per second. Okay. This is MD. Now the back EMF, EB we know it, K phi into omega. Omega is the, phi is the flux. For a machine, this is constant K phi. Okay. So K phi, we can also, phi we are keeping it constant by fielding the, giving the correct excitation winding, and K depends on the machine parameter. This we have talked about in the last class, how to find out. Now, the driving torque MD, MD is also equal to K phi into our IA in Newton meter. So, from these two relations we can bring in the speed into our original equation, and we can find out, because that is the speed is our output, input is the armature voltage. So, we should have a relation between these two. How to find out? Now, let us take the previous equation, armature voltage equation, that also we will write it here for clarity, so that again we can refer it. VA is equal to IA RA plus LA DIA by DT plus EB back EMF. Now let us take the let us write in time domain the Laplace domain this one. So that will take care of the frequency part. So this will be equal to our armature current. IAS is equal to VA minus EB divided by RA plus LA into S. D by dt we represent the S. So this can be again rewritten, modified. So from this one, again we can modify this equation, that is AS is equal to VA. Now we will bring the EB, this one we will bring it here. EB is equal to K phi omega into S, okay, divided by RA into 1 plus LA by RA into S. So this is in the time constant form, 1 plus ST, that form. Okay. Now omega ms, omega S is equal to our MD minus ML divided by JS. Okay. This also we can write MD is equal to K phi into IA. Here this we can bring it here, this K phi IA. So this will be K phi into IAS minus our load torque divided by J into S. S is our Laplace. Okay. Now based on these equations, let us see whether we can write down the input output transfer function or the block diagram of our DC motor. So let us go to the next page. So before coming to the block, let us again, for our reference, let us write down our voltage. IAS is equal to VA minus EB divided by 1 plus RA into 1 plus LA by RA into S, that is one equation. Omega S is equal to MD minus ML by by Js, okay, and MD is equal to K phi IA, okay, and EB is equal to K phi omega omega. So, let us write down our transfer function. How do you do it? No, sorry, the block diagram. So, we have VAS, we are giving here, and if you see VA minus EB, so this is plus, this is our EB, VA minus EB, we are, this has to be multiplied by 1 by this one. So, this we can write it like this, 1 by RA divided by 1 plus, what is LA by RA? LA by RA is the armature time constant. This we can write as TA, it has a unit of seconds. So, 1 plus TA into S, 1 plus ST form, okay. Now, what is this output? This output is our current IAS. So, this IAS into K phi, so gain function, into K phi, this is our machine, is will give our driving torque MD. MD. So, MD minus ML, MD minus ML multiplied by 1 by Js, this give our speed omega s. So, this is our omega s speed. This omega again multiplied by this K phi, your back EMF. So, this is our motor model. Now, what we want the transfer function? Input output relation, we want the omega s speed, our control variable is VAS. So, we want a relation between the omega s and VAS. Let us write down the omega s by VAS of the form GS by 1 plus GSHS. So, what is GS here? GS is equal to K phi divided by RA plus Js into 1 plus STA, okay, divided by 1 plus GSHS, HS is only K phi. So, here if you say here 1 plus GSHS, here it will come K square phi square divided by RA, then again divided by Js into 1 plus STA, okay. So, this again we can simplify, and this we will get also equal to, we can bring this one up. So, this will be K phi by R A divided by this one multiplied by 1, J S into 1 plus S T A plus K phi square divided by R. So, again we can bring into the standard form if you take the denominator, that is 1 plus S square S that time. In that form, if you want to bring it, this can again we can write it as, this is equal to, we are dividing the whole thing by R A by K phi square by R A, we are dividing that one. So, this will be equal to, when we divide this one, the numerator will be 1 by K phi, this is the numerator, denominator will be J R A by J R A by K phi square into S into 1 plus S T A plus 1. Okay. One plus S T A into. So, this one, what is the unit of, can we write this, this will have a time constant of seconds, this also another time constant, and it is called electromechanical time constant. So, final transfer function will be 1 by K phi divided by S T M into 1 plus S T A plus 1. So, T M, our T M is equal to electromechanical time constant J R A by K phi square. How to find out? We can put the values, the units here, and we can find out this as a this unit of seconds, and we can also electromechanical time constant, because electrical side R A is there and J is there, that is due to the mechanical moment of inertia. So, that is called electromechanical time constant. This also we can verify how electromechanical time constant. Let us assume the load torque ML is 0. And let us say we are applying the full voltage VA to the machine. Okay, and let us also assume we are giving the full current, controlling the current, so that always it is giving the maximum torque to accelerate. So, VA is equal to, then it will be K phi back EMF, it is a function of omega t, function of t plus IAR. So, here we have the L part we have inductance part we are removed, because we are through controller we are giving full current, we are controlling the current IA and applying the VA, full DC we are applying that one, assuming the leakage inductance is negligible. Now, L is equal to 0 dl. So, the torque, driving torque MD is equal to, for acceleration, J into d omega by dt. Okay. This is equal to K phi into Ia, K phi is constant, this is our driving torque. Now substitute this one to the equation, Va is equal to K phi omega t plus, now let us take what is this Ia. Ia is equal to J into d omega by dt. From this equation, Ia is equal to J into d omega by dt divided by K phi. So when we substitute here, this will be equal to JR by K phi into d omega by dt. Okay. So we are applying the voltage, and leakage inductance we are neglecting, and we are giving the nearly constant current. So full driving torque we are given, and the machine is accelerating. Okay. Once the speed reaches the full speed, let us divide this one by Va by K phi. Va by K phi is equal to omega t plus JR by K phi square into d omega by dt. What is Va by K phi square? When d omega by dt will be 0 when the machine has reached the no load speed, full speed. Then omega t, that no load speed Va by K phi, that we have derived in the last class. So Va by K phi is equal to omega no load, that for applied voltage what is the maximum speed it can go. Omega no load is equal to omega t plus JR by K phi square into d omega by dt. Okay. So this is of the form omega t plus time constant Tm into d omega by dt. So the solution will be omega t will be equal to omega 0 into 1 minus e raised to minus t by Tm. So this is the time constant. So this is called the electromechanical time constant. So let us introduce the electromechanical time constant into our system and then modify our equation. Now we know it's Tm is equal to J Ra by K phi, that K phi we will take as machine constant, we will take as Km, we will simplify. So J Ra by Km square. So we want to introduce a Tm here. So J we can write in terms of electromechanical time constant, Km square divided by Ra. We know that omega s is equal to K phi. K phi is equal to Km into Ias divided by Js minus, that is a Md minus Ml by Js. Okay. The moment introduce J here, this J here, this will be Km Ias is equal to we are trying to introduce this one J here. So this will be Km into Ra by S into Tm into Km square. This is, we substitute J from here, minus Ra by Km square into Ml minus Tm into S. So finally the omega S is equal to Ra by Km into IAS minus ML into Ra by this Km and Km goes, that is why Km here, Ra by Km square into 1 by Tm. So, with this one, so the whole purpose was to introduce the electromechanical time constant. The J factor is also inside this Tm. Now, let us rewrite our block diagram and modify, find out our transfer function. Let us say this is our VAS, VAS, here one by Ra divided by 1 plus TAS this is our IAS. So, from the previous equation IAS into Ra by Km is equal to MD, Ra by Km, this is our MD, driving torque, plus minus ML into Ra by Km square. Okay. Into, so sorry here, one by TMS, this is our omega S speed. That K5 we have taken as Km now, this is the back EMF. So, this is the back EMF. So, we will get the transfer function same as like previous, we have derived it, omega S by VAS is equal to GS by 1 plus 1 plus GSHS 1 by Km divided by GS is 1 plus STA armature time constant into electromechanical time constant 1 plus TMS GS by 1 plus GSHS, that is 1 plus Km into 1 by Km, this will get cancelled, divided by 1 plus STA into STA. See, all this exercise is to represent this transfer function in time constant form, that is 1 plus STA into 1 plus ST B into ST. So, time constant form we have to do it. So, why it is required? If you know the time constant form, if you put it, we know which time constant is the largest time constant. So, that will delay the system. So, we can use a controller to, if I use a PI controller, the 0 of the PI controller can be chosen such that this large delay can be cancelled. So, delay means there is a lag, it will introduce a lag. So, the moment you will give a 0 means it will give the lead. So, this lead and lag will try to compensate the total system of the delay, we can try to compensate, that is the purpose. So, this will be finally of the form, this will be equal to 1 by Km divided by 1 plus STM plus S square TA TM. See, this is not the time constant form, this is not in the time constant form. So, here we will we know that the TM Tm is much greater than, let us take the condition where electromechanical time constant is much greater than Ta. For example, if Ta is in millisecond, Tm can be in seconds. So, Tm we can assume Tm is much greater than Ta. So, this 1 plus this 1 plus denominator Stm plus S square Ta Tm, we can approximately write as one plus S into Tm plus Ta plus S square Ta Tm. See, we are not disturbing this Tm, we are only say small, to the second we are adding only a millisecond. So, this more or less Tm only, but when you do this one, the final transfer function we can write it like this. These are simple approximations to get the transfer function in a proper form. So, 1 plus S into Tm plus Ta plus S square Ta Tm will be equal to 1 plus Stm into 1 plus Sta. So, we got the thing in time constant form, 1 plus Stm, the standard form, okay, the pole 0 form, okay, 1 plus Stm. So, if you do this way, the final motor transfer function, input output, that means we are giving Va, see all these blocks we do not require now, we are only looking at the output Vs with respect to omega s. So, omega s by Vs will be, final transfer function will be, let us go to the next page, final transfer function Vas, sorry, omega s divided by Vas is equal to 1 by Km divided by 1 plus Stm into 1 plus Sta. So, if you are controlling the speed omega s with the Va, the response of the machine depends on two time constants. One is the armature time constant Ta, one is the electromechanical time constant Tm. Okay. So, these two Tm and Ta will determine the response of the system. These are the time constant of the system. Now, let us go back to our original diagram. That is, we have applied the speed control, that is NR, reference speed. We are getting speed feedback. See, these are all voltage levels for controller, we are bringing it down. So, this will go to a controller, this controller output will control our firing angle. Let us say the firing angle cosine comparison EC. This we have to give to our converter. This converter output give the required Va, armature voltage, and this we are giving to motor. So, motor transfer function we already got, that is 1 by Km divided by 1 plus Stm into 1 plus Sta. This is our omega s. Now this omega s will process it to bring back to the controller level filter. This is our speed control system. But let us say the machine is at standstill, it is not started, and operator gives a speed command. Operator doesn't know all those things. He will give a high speed command. Let us say motor has to go to the full speed. So full speed is represented by plus 10 volt. So let us say it's 10 volt is given. And machine will take, because mechanical time constant, it will take its own time to speed up. But the controller are very fast. Feedback is 0 initially. So what will happen? This will ask for the full control output EC. So that we want full control output means if for a 3-phase control rectifier, it is proportional to cos alpha. So cos alpha is equal to 0, cos alpha is equal to 1. So EC will go to the required controller so that the converter should give the maximum voltage. So we will be applying the maximum voltage here. So let us take a case, an induction machine. We know the speed is proportional to armature voltage. So we want a full speed, machine is at standstill and we are giving full voltage. So what will happen? There is no back EMF. If you go back to our previous equation, the armature voltage and armature current, back EMF is not there. So the full applied voltage has to be dropped across the resistance and the leakage inductance. So what happens? Full voltage is applied to the machine. So heavy current will flow initially. So sometimes depending on the applied voltage, the current can be beyond the rating of the machine. So till it speed picks up, the current will be going and the winding will get up, sometimes get heated up, and the machine can get damaged. So here the problem is current is not controlled. We are only looking at the speed and the voltage. But what is the machine current requirement? For a machine there is not only the voltage rating, there is a current rating also there, maximum current rating, okay, or short time overload. We cannot exceed that one. So any speed change, any speed control also has to have a current control to take care of the motor. So that part we have not put here. So from the converter and controller inside the machine, from V8 before going to the machine, there should be a current control loop is there. What means? The VA applied voltage to the machine now is not dependent on the speed error. Applied voltage also has to be dependent, it has to be dependent on the present current available to the motor, or we should always see to it that VA is applied such a way the machine during acceleration and deceleration, during giving positive torque and negative torque, machine should not be drawing more than the maximum current. So there is an inner current loop is required. Same like our phase control converter, outer voltage loop and inner current loop. So there is an inner current loop, fast acting current loop, because that has to be very fast. Because any change in the omega s depend on the mechanical time constant. So VA has to be controlled depending on the current requirement of the machine. So we have to modify, alternate this block diagram, and we have to introduce the inner current control loop, and then we have to find out the controller. So what should be our current control loop? That means our VA, armature voltage, should be controlled according to the current in the machine. So let us take our IAS is coming, IAS. Okay. IAS reference is there. So from where this IAS reference comes, we will come to that one. So IAS reference, that is a reference current. So this reference current we are putting so that this maximum and minimum positive and negative limit of this current for positive torque and negative torque depending on the machine rating. So, there should be a current feedback from the machine. So, here also we require a controller. So that if the current exceeds the rated current, this controller should act and bring back our armature voltage. Okay. So, this armature voltage depend on the current reference. So, we have to control the armature voltage in such a way, as I told before, for fast dynamics, machine should be always drawing the maximum current, maximum torque, maximum positive torque and maximum negative torque depending on the current rating of the machine. So, VAS, applied armature voltage, should be based on the current controller. Okay. So, again if you write down the machine model, this is our EB. So, this transfer function is equal to 1 by RA by 1 plus STA, then this our, here is our actual IA, this we have to feed back here. So, this current from the machine, so it will have, you have to step down, and because of the switching there will be ripple will be there. So, here we are dealing about DC current. So, there should be a filter also required here. So, this will go. So, what is the transfer function for the filter will come, simple first order filter we use. So, IA is required. So, this inner current loop is required. Now, this IA divided by Km is we know our driving torque. Okay. So, minus ML into RA by Km square. We have brought the electromechanical time constant into picture here. Then this is our 1 by TMS, this is our speed omega s, this is the output what we want. Now, this output again will put filter and give to the speed reference. This is our N feedback. Okay. So, previously this controller output was coming from our speed reference and speed controller. Okay. Now, this controller VA is controlled by our IAS reference, IAS feedback. So, where the IAS will come? This IAS should be the output of our speed controller. Previous speed controller. Now, the speed controller output, speed control output is not directly connected to VAS. Previously, the speed control output was trying to control the VAS. Now, the speed control output is controlling IAS. That is true also if you see here. Why there is a speed in change, reference speed and set speed, when the driving torque is not matching with the load torque. So, we have to give the correct torque. Where the applied voltage, armature voltage, VA we are controlling to get the correct current. So, this is a intermediate variable. The direct variable what we want is the current. Any speed, any change in the speed, that should reflect on the driving torque. So, that means driving torque means it is K phi into IA. K phi is constant. So, you should, the system should give the correct IA, and for that IA we have to control the VA. So, based on this one we will formulate the complete closed loop diagram in the next class, and we will try to design our controller. Now, we have to design our current controller and the speed controller. Once that is designed, then we can go for the actual implementation. We can simulate also, then see the response and go for the actual implementation. This we will study in subsequent classes.